Here we have our home heater controlled by this remote control, which we are not going to be touching at all. And here you can see we have our setup with our basically IR sender and receiver and a temperature sensor that's measuring the temperature as we go. And if you come look at our terminal over here, you'll see we're currently running this code and it's printing out a couple values. We have set up a geofence around the apartment, or in theory, it would be around the apartment. And the purpose of this geofence is essentially that every time you enter the geofence, that you can set the radius yourself, you will basically be in the range that we've identified as time to turn on your heater to preheat your home. So, for example, let's say Rishi's walking home from class and he enters the radius. What will automatically happen, maybe 5 minutes before he gets home, is the heater will automatically turn on the moment he enters that geofence, and it will start preheating the room for when he gets home. And then, kind of working inversely, if Rishi's leaving his home and he actually left the heater on, the moment he leaves the geofence, it'll automatically turn off, which hopefully works to conserve some energy.
Yeah, thanks, Dylan. So as you can see from my feed, I am not at home right now. I am actually on static ad. All right. Yeah, so this is an app called IFTTT. And in this app, you can do a lot of automation tools. So in my case, I want to automate, when I cross a geofence, I want to make sure that it will trigger the heater to turn on or off. So I have this one here. If you enter an area, then send data to the thermostat geofencing Adafruit IO feed. So this will actually send data to Adafruit IO, and then the code will actually pull from that cloud and use that data to determine whether I'm inside or outside and turn the heater on or off accordingly.
And just before Rishi shows this, recapping the values, you'll see in the terminal we're still reporting outside the geofence at around just under 75 degrees. So we'll see how that changes when we enter the geofence.
So I'm crossing into the geofence now. It's pretty fast. We'll have to wait a little bit just for the data to send over, but we'll expect to see. Now I'm going to the geofence. The program knows I'm getting home. I'm coming home quickly. So it will turn on the heater based on the amount of error between the current temperature and the reference. So I think Dylan said it's around a 5-degree error, which means the heater should turn on to heater level 2, which you can see in our code. And I think, as we can see on Dylan's side, the heater has turned on and switched to level 2.
There.
So I have this other IFTTT, which is for exiting an area. So as you can see, I'm crossing the geofence. I'm actually crossing it right now. So we'll expect to see the opposite thing.
And there you go. And now if we go to the terminal, we'll see in just a second here that it will be reporting outside the geofence just like that. And therefore our heater is turning off, and this is the 30-second countdown to turn the heater off.
In the previous section, Dylan alluded to how our IR system works. So basically, you point the remote, press a button, and that signal is put into raw data that is received by the transceiver breakout board. We can analyze that raw data and reconstruct the signal and transmit it back to the heater. But that doesn't really tell us much about when we should be transmitting these signals. What's the logic behind that? So that's what this section is about. Now, we already said we want an ultra precise heating system. Now, the thing is, a lot of heaters commercially available, they can only get to like 1 to 3 degrees of steady state error. But we want to do better than that. We want to make it as precise as we can. But we don't want to sacrifice rise time or introduce overshoot into our system. So that's our challenge, to beat the market and design a better thermostat system. The way we should do that is by talking about control theory. So here on the screen, I'm showing a PID control, which is a very common type of controller. But basically, control design is all about you start off with some value, some state value, and you want to get it to some reference value. Basically, a controller should take the error and do something with it such that you drive your system to that reference value. Now, we don't know much about our thermal system and how it'll behave. It's kind of a black box. So we're going to start with a very simple controller and scale up from there based on how the response is. So it's a very iterative process, and we just keep on testing responses until we get the one we like. Yeah, and on this plot, you can see our results. So first, with the proportional control, you can see it wasn't bad, but we still had a steady state error of 1.5 degrees Fahrenheit and a rise time, which is very long at 53 minutes. We can do better. We're trying to beat the competition here, and right now we're kind of matching it in steady state error and lagging behind in rise time. Then we tried integral control, and here we met the reference temperature actually, which is what we'd expect from integral control. However, the overshoot was now non-zero. In fact, it was 3.5 degrees Fahrenheit, which is a lot. Finally, we introduced anti-windup. And we also changed the Ki parameter to be 0.005. And this got us exactly where we need to be. We have no overshoot. We have a rise time of 15 minutes, which is like the amount of time it takes me to get home from campus. So it works great with geofencing. And steady state error, incredibly, is 0.05 degrees Fahrenheit. It is basically dead on. And this is significantly better than even the best commercial thermostats out there. All right, so just to prove that we didn't just pull these graphs out of nowhere, here is me actually in my bedroom. You can see my bedroom here, which is the thermal system that this project is trying to regulate. So here you can see me actually testing the PI controller here. And you can see from the console that we have the temperature error listed, the controller input, which is directly controlling the actuator, or in this case, the heater. And then we have the integral error, which is accumulating the error over time with anti-windup built in, and the reference temperature and temperature. So you can see here, we got the system right here. So yeah, this is me actually testing it. You can see the data is not fake. We actually have been able to achieve a controller for our heater and our thermostat with a steady state error of basically 0.1 degrees Fahrenheit, if not less. So first demo we're going to show you is the NeoPixel. The NeoPixel, we've developed a function that actually color maps certain colors to certain temperatures. So it's about 76.5, and the function maps that to about a greenish color. And we'll see right here, it's a little hard to tell in the camera, but that is very definitely green. If we go into the code and we actually change the function parameter, instead of taking the sensed temperature, we'll just put in, like, let's say 80, which the color function should map to orange. So let's run it. And let's point at this. Yeah, you can see, right? So it clearly turned into a much more, I guess, orange shade. Let's try 60. This should be like a cold blue, like a really saturated blue. And boom, we get a blue. So that's how the NeoPixel works to tell you temperature. Because we are inside the geofence, you can see that the red and green LEDs are active and the green one is on because we're inside. So now let's say I want to go outside. So let me hop outside real quick and we'll see if the red one turns on like we expect it to. All right, so here you can see our humidity sensor setup. We currently have the proto board attached to this area right above the stove, and this is in a prime position to detect any humidity changes. You can see we have the sensor right here and the battery pack here when we don't have USB. However, in this demo, we do have USB because we want to show you the serial monitor outputs. You can see it's actually recording and displaying the relative humidity measurements, and it's showing that next to a state variable reading, which is showing true and false. Right now it's showing false because it's actually representing the window state. The window is closed, it's going to be false. The window is open, that will be true. And this is important for actuation and determining if certain criteria is met to actually open the window. So right now nothing's happening because there's no cooking going on, and that's good. But what happens if we actually take some water to simulate cooking and increase the humidity that way? Let's see what happens. So on the serial monitor, you'll notice that soon the humidity will spike, and then we'll see a retract signal sent over to the actuator. So if we go over to the actuator, you'll see that within a little bit of time, it starts to actuate and the window is actually opening. So now let's see what happens if I take the stove off, I turn it off, and we should see a shut signal being sent. So let's see what actually happens.